I would like you to write down a definition for the word equilibrium. I'm going to give you a minute or so to write down a definition for the word equilibrium. Okay. Did you come to a consensus at your table? Are you fighting about definitions? It's getting heated over there, David? What did you guys say? What was your contention, or what did you guys discuss?
When an object has a net force of 0.
What do you think? Do other people agree with that? Anybody else say that? Raise your hand if you said that. Raise them like you care, like you're proud of it. Yay, me. Okay, lots of hands said F net equals 0 or some form or something of that. What else did you say if you didn't say that? I'm curious. Not everybody their hand up, or some people are like, I kind of had my hand up. What else did you say? Oh, come on. You didn't all have your hands up like, yes, that's exactly what I said. Caleb, you were like that when I asked. What did you say?
I'm just thinking like an object can have net force of 0, but it can still be moving, so it's not necessarily at equilibrium. So I don't know if that does that count.
I don't know. That's a good question. So say that again. Say what you just said one more time.
An object can have a net force of 0, but it can still be moving. So is it still at equilibrium, or is that somewhere else that has like a force pushing it back and forth, like restoring?
Ah. Thoughts?
When there's no energy, when the object has no energy.
No energy? Sounded like you said that with a question mark at the end? Or did you say that with a statement at the end?
Statement.
A statement at the end.
Yeah. No kinetic energy. But it can have potential because somehow a spring has potential energy, but there's no kinetic. But it's at equilibrium. But it's just hanging there.
Can it still move? Like oscillate at a constant speed?
Not sure.
Well, I don't know. That's why I'm asking, right?
On object on a string, then it has potential because the string has potential energy.
Okay, I want to go to Mira, and then I'm going to come over because I want to know what that was going. What did you say?
Oh, I said that it could be oscillating at a constant speed. Therefore, it still has kinetic energy.
Okay, let's back up for just a second. She said it can be oscillating at a constant speed if an object is like on a spring, right? Is that what you're saying?
Yeah.
If an object is oscillating on a spring,
It's going.
is its net force 0?
Because the acceleration is 0. Oh, so.
Is the acceleration 0?
Well, its net force isn't 0, but it's not exactly always at equilibrium.
Yeah, it's going through equilibrium.
But like when
Okay, so what is equilibrium?
when it's at just a point where it's not, there's
Yeah, it's
there's still movement, but there's no.
Oh, so it's going back and forth on the equilibrium position. Is that what you're saying?
Yeah. So like, I mean, it can be like there's like velocity at the point, but there's no force, so there's no acceleration. That's what we define as equilibrium.
In that case, right?
Case, yeah.
Do you guys understand what he's saying? So like if we think back, I'm going to bring back that picture that we had, I don't know, forever ago. Was this it? Not that lucky. Where did that picture go? No, I thought it was on this page. No. Similar quantum motion. No. I don't remember where it went. Where did that chart go? Do you guys know what I'm talking about?
Yeah.
Oh, similar quantum motion analysis chart. Here.
There it is.
That's what we're talking about. Okay, so when you did this, where does equilibrium exist in this story?
The dotted line.
Right here, right? Does that match with what, like, does that jive with everybody's brain? Is that okay? Okay, so that's equilibrium. Why is that equilibrium?
Because if the weight was, I know it's gonna oscillate a little bit, but put a weight on the spring, it's gonna be, and you just let it hang there,
Mm-hmm.
moving, that's equilibrium. But if you pull it down from equilibrium, then it's gonna start oscillating.
Mm-hmm.
Yeah. So it's, I don't know how to explain it, but that's equilibrium at the point where both energies are being canceled, so the gravitational energy and the normal force of gravity and the normal force of the spring, or the spring force, is equal to 0.
Okay, so in it, like, because this one's horizontal, you can do that, or you could do the vertical. It doesn't matter. You're saying that here is the place where what?
Where it's basically F net equals 0, or there's no energy. Well, there's potential, but I don't know.
Go here, and then we'll go back here. Go. And David will get to you next.
Well, we said, or we, this is the one I had to review. It said, the displacement is neither positive or negative.
Where the displacement. Say that one more time.
The displacement is neither positive or negative, like if the displacement is 0.
Okay. Go Chris, and then Jordan, and then David. Go.
It's the point that an object is always trying to return to.
This is so cool. Go Jordan.
Something like that, and it's the direction that the potential energy, it's where the potential energy is 0, and where the potential energy is the force, the applied force is always bringing it back to, like, the force of a spring is always pushing or pulling it towards equilibrium.
Okay. Okay, so that's kind of like this thing.
Yeah.
Okay.
I think they covered what I was gonna say.
Okay.
But what if it's just going on forever? Like it just keeps going and it's at its equilibrium? You know, like the balls, and then you pull them and then they.
The schwanky ball. Yeah.
Yeah. What is I can't remember what that's called.
Newton's
But then
cradle.
it just keeps going. Yeah. It just keeps going forever. If there's no air resistance,
Yeah.
would that be considered equilibrium?
What do you guys think? So like a pendulum is kind of what you're saying, right? Like
Yeah.
let's simplify it a little bit. So instead of having the Newton's cradle, what if you just have one object on a string
Yeah. And
Yeah.
it just keeps going.
and it keeps going forever? Let's say that there's no air resistance, right?
Yeah.
So where is equilibrium in this case?
At the very bottom.
There was no applied force besides you holding it.
No,
Just when it makes equals.
So it's just
Like
one.
but the force of gravity is bringing it
Yeah.
down until it's at that bottom point.
Right?
Oh.
Where the restoring force is 0.
So what did you say?
Where the restoring force is 0.
Where the restoring force is 0? So I have to say, it's kind of interesting. As a teacher, I don't know if you guys know this. This is like in the mind of a teacher, right? So like I plan to have this conversation, and I just plan it by asking, like, I'm going to ask this question and then see where it goes, and then da-da-da. This is absolutely not where I thought this conversation was going to go at all. It's so cool. I'm so excited. No, like it was not in my head. All of this stuff, and I love it. All of this stuff goes back to like the simple harmonic motion stuff, right? You guys are like totally in simple harmonic motion mode, which is so cool. And that's not where my head was at all. So did we talk about equilibrium ever before simple harmonic motion?
Yeah.
I know we did, because I know you guys got mad at me because I used the E word and you're like, wait, what does that mean? I'm like, yeah, we've talked about this for a million years, but we just never have used that word. We just talked about it in terms of this thing. Like, the second day of school. Like forever ago. Like a really long time ago. Yeah. Like, I'm sure I could probably find some problems way back here. I don't know, like mystery boxes maybe or something. I don't know, like finding friction and all of that crazy stuff. I was going to try and find something that was good. I don't know, like this one. I don't know if you remember this. This was like in what?
I do.
September 4th. Whoa, like forever ago. A spaceship and 4 cargo pods are connected together by these things, blah, blah. It's at a constant velocity. Talk about the tension. Does this sound at all familiar? And we were talking about these things, and I'm not going to go back through all of this stuff. Whoa, so long ago. But this is where we really started with this statement, was this F net equals 0 business. And that's where we got to from the simple, like that's where we got it from for the simple harmonic motion stuff. Now I have a question. Can something be moving and at equilibrium?
Yes.
Yes, she says. For example,
With the constant acceleration.
you're really close with a constant something.
Velocity.
Constant velocity, right? So we can have kinetic energy. Okay? It just has to be at a constant velocity. Constant. Because if it had a constant acceleration,
That's what I meant.
I know. And that's why I'm poking you. If it had a constant acceleration, then what, Isabel?
And then the acceleration is zero.
Acceleration is 0.
If the acceleration is constant and not 0,
Wait, what was your question?
I don't
Wait,
remember.
you said velocity is constant?
I think velocity is constant.
Then
Before
acceleration is
you said that, you said that the acceleration was constant.
That's wrong.
It is. I want to know why it's wrong.
Because then, unless the mass is 0,
Then what?
then it would have a force of 0. F net.
I
Like,
connect those dots for me one more time because I got lost on a turn there. Okay, so let me ask it again. If it's an equilibrium, you said erroneously, and we all agree on that now, that it would have a constant acceleration. And then you said, wait, that's not right. Why is that not right?
because I'm just thinking backwards now, but I'm thinking like,
Can I think with you?
I guess, yeah.
I suppose you can come with me. So if the acceleration is not 0 and it's constant, what does that mean? That what? That F net is not 0.
So there has to be a force being applied for it to accelerate.
And if F net is not 0, then what do we know for sure about whether we're at equilibrium? We're not at equilibrium. I just want to make sure that really makes sense. This is like so important, right? Acceleration, velocity, not the same thing. We know that, right? Okay. In this case, the story goes that something's at equilibrium if F net is 0, which means that either it's not moving, which means it has a constant velocity of 0, or it's moving with some other constant velocity that's not 0, but it's not speeding up or slowing down, right? Are we okay with that?
Yeah.
Okay. All right, that's fun. Now, I'm going to tell a story. It's a story about Jordan and Emily. Jordan and Emily are buddies. Did you know this? And Jordan called up Emily, and she's like, Emily, you should totally come over to my house and help me rearrange my living room because I blah, blah. I don't know the whole backstory to it. But for some reason, Emily needed to come over to Jordan's house and help her rearrange her living room. I don't know. I didn't ask, but this is the story here. And the big issue was that Jordan has this enormous table in her living room that she needed to move, right? Yes, I do, yes. And she needed help moving the table. And so Jordan was standing over in the middle and she was pushing on the table. She was applying a force to the object. It was enough to overcome, no, it wasn't enough to overcome static friction. She pushes. She pushes harder, it doesn't go anywhere. Emily, come help me. So Emily comes over and she says, okay, I'll help. So Emily and Jordan have about the same force, we're going to assume, applied force, maximum applied force that they're able to push with. So Emily comes over here and she pushes, and Jordan goes over here and she pushes. 1, 2, 3, push. Oh, it moved. Yay. That's a good story, right?
Yep.
So at the beginning, when Jordan was just pushing, what do you know about the table? It was at what? It was at equilibrium, right? And then, well, that's not helpful because it's not going anywhere. Then Jordan's over here and Emily's over here, or vice versa. I can't remember which way I set it up a minute ago. But anyway, they both push, and now the table is definitely not what? Life is good. Until Jordan makes some snarky comment that upsets Emily. It's never a good thing. You don't want to upset Emily. Now, by this point, see, I forgot to add this piece in. When they were pushing the table initially, it was on carpet. And carpet, we might imagine, has a little bit of a higher coefficient of friction than the wood floor on the other side of the living room. Okay? So they both pushed and they pushed and pushed and pushed. And now it's on the smooth surface. So now Jordan really could push it by herself. She doesn't really need Emily to help her anymore. But snarky comments start flying. Gets a little ugly. These two, like, they seem really friendly, right? They seem like they get along. They seem like there's no problem. Watch out. Okay. So, who did I say made the snarky comment? I don't remember. Was it Emily? Oh, it was Jordan. Jordan makes a snarky comment. Emily's like, forget this. I don't want to help you anymore. And in fact, not even do I not want to help you anymore. I want to make your life hard. So Jordan's like, I still need to push the table. And now I have the ability to push the table because it's on this nice smooth surface, right? But Emily's like, not so much. So Emily walks around to the other side of the table. Daisy, can you imagine this? Is this something? She's like, I've lived this. I know exactly. Right? And so Emily is pushing this way, and Jordan is pushing this way. And they're doing like a thing, right? Like you can see their faces. Like, and they both apply the same force. So once again, what can you tell me about the table? It's at equilibrium, right? Okay, so then they're just doing that, and then, like, that's going to be fun for a long time. Yay, now Jordan is like pushing and her face is turning red, and Emily gets this little, it's like one of those cartoons where the light bulb like pops up above her head. She's like, I just want to make Jordan's life a little bit less fun. Even than just her face turning red and like the veins popping out and all of this stuff. So Jordan's like, and Emily's like, and then Emily takes a step over like this. Except she's going over there, right? And she's going to push on the table. So Jordan's still here. She's really not paying attention to anything else because she's just mad. She's just pushing really hard. And Emily stands over there at the corner and pushes this way. What's the net force acting on the table? What is it, David? What's the net force on the table? What was the net force when Emily was there and Jordan was here and they going at each other? Net force was what? 0. Emily takes a step that way and continues to push really hard, and Jordan's still here pushing really hard. What's the net force acting on the table? The net force is still the same, isn't it? But what?
They're not pushing in the exact opposite direction.
But Jordan is pushing this way and Emily is pushing this way. Those are opposite directions.
Okay, like compared to the center of gravity of the table.
Something's weird's going to happen though, right? What's going to happen to the table? It's going to start moving in a circle. Does that make sense? Okay? What's the net force acting on the table? 0. Is the table at equilibrium?
Yes.
No.
I'm asking, I don't know.
If it's at a constant
I was so sure about that.
What are you sure about?
But if it was at equilibrium.
It was at equilibrium. Is it at equilibrium now? Yeah? What's the table doing?
It's moving at a constant velocity.
It's moving at a constant velocity?
Maybe.
Possibly.
I feel like the
velocity.
Fnet can't be 0 though.
Overcome
Because it was not moving at all and now it's going to start moving, so that means that there's a change in velocity. So it has to accelerate at least a little bit because the table isn't massless. So it has to have some F net that isn't 0, but I don't know how or why.
What do you think, David Jordan?
What?
What do you think?
I agree that it is at a, I don't know. If it is at a velocity of 0 and then moving at a constant velocity, there'd have to be some change. So I think like once you get it past the coefficient of friction has something to do with it. I'm not sure.
No friction. We don't care about friction.
Okay.
We're on a really smooth surface now.
I'm lost.
You were close though. Of course I was. Of course I was, he says, with complete modesty. Where's the table? Is the table actually going to move anywhere, really?
Well, it depends on what part of the table you're talking about. Because the table is moving if you're talking about the right leg over there.
Okay.
Because it's going to move in a circle.
But it's going to move in a what?
Circle.
It's going to move in a circle. So if we just keep doing this forever and ever and ever, and Jordan's like really not paying attention, and she's just walking in a circle now. I'm picturing like some sort of really bad like Looney Tunes cartoon, right? And I think this could happen. Okay, and so maybe it would be better. Let's take a step over here. So Jordan's pushing over here, and Emily's pushing over there, and they just keep pushing and pushing and pushing and pushing. Have you ever been in a situation where you're pushing on one end of something and somebody else is pushing on the other end of something? Yeah, like probably a lot. Where have you had this experience before? Maybe there's some sort of axle in the way. Yeah, a rotating door, right? So if you're standing in one side and there's somebody else standing on the other side, you can both go where you want to go, right? And as that door rotates, is it moving? Does it have velocity? Is it like going anywhere?
Oh, no.
That would be frightening, right? Like, oh, there goes the door. Whoa. No, it doesn't. I mean, like, it's bolted down in the middle, right? But there is some sort of something, right? Because it was sitting at rest, and now it is
Same.
moving, but it's not the same kind of thing.
I think you have to define like what the system is.
Yeah.
The system's a table.
The axis is
Okay, but is it the whole table? Is it the leg of
They're
the
not
table?
changing how much force
Is
they're
the
using.
center of the
Okay, let's have one conversation. What
They're
now?
not changing how much force they're using.
No.
It's the same.
Same number, same amount of force.
Yeah, so then it's at equilibrium.
So it's at equilibrium.
Yeah.
Okay. Do you guys agree with her?
Yes, the equilibrium.
I don't know. I don't think it's fair to say it's at equilibrium. I don't think it's fair to compare it to pushing it this way. It's completely different. I mean, it's,
How so?
well, like the point.
Okay.
I mean, so let's say there's like, obviously like the door's here, but then it can move from here to here. So it's got its own direction. It's just in a circle, not just this way and that way.
Does it depend on direction?
I don't know. Okay, I think I hear what you're saying, that there's some sort of motion going on, but it's not straight line motion?
Yeah. It's,
Okay, let me write that down, and then I'm going to come right back to you. So I'm just going to write down, there's like a different kind of motion. Besides straight line. Go, Allison.
Okay, so we've all agreed that you're traveling in a straight line at a constant velocity, and F then what if it was rotating at a constant velocity? Then could F net still equal 0 and then it could be equilibrium?
Yeah.
Yeah, but it's not at a constant velocity. Well, like, it could be eventually, but because it wasn't moving and then it is moving, there's for sure a change in velocity, so there's for sure an acceleration happening at some point in time. It might then, like, go to a constant velocity, but there's certainly a point where it isn't, I think.
You okay, David?
Yep.
Are you sure? Can you tell me what's going on in your brain?
Can't.
He just says one word. Can't.
I can't.
Are we like talking after the thing starts moving or from rest towards the...
Well, that's a good question, right?
Oh boy.
So you get to pick. Does it matter? Let's assume for just a moment, let's assume that there is no friction between the table itself and the ground, okay? But that Emily and Jordan have shoes that have like nice, like, you know, are able to have friction. Because otherwise they wouldn't, like, none of this would be happening because they wouldn't be able to push either. Does that make sense? Because when they push, they would just go backwards and then it wouldn't, like, then the story isn't even a story anymore. So they're not going anywhere, but the table has no friction. Okay? So they step over to the sides and they start to push with the same amount of force. Jordan's pushing over here. Emily's pushing over there. What's going to happen to the table? They're going to keep pushing. They're going to keep walking. What's going to happen to the table? Is it just going to start moving at a constant speed? I don't know. This is kind of weird, right? Is it accelerating? You say yes?
Yeah.
How many of you think that there's some sort of acceleration going on? If there's some sort of acceleration going on, then what do we have to say about this equilibrium thing? Is it an equilibrium?
No.
No, if there's some sort of acceleration going on with this some sort of different kind of motion, this is a big deal. This is like, welcome to this unit, chapter or unit 5. Okay? Different kind of motion. Okay? Instead of this straight line motion business that we spent an entire semester on, let's talk about a different kind of motion. What kind of motion are we talking about here?
Circular.
Yeah, moving in a circle, right? We could call that rotational. So, in that case, this says, we said earlier that F net had to equal 0 in order for something to be in equilibrium. Is that the only part of the story? Is that the only thing that has to be true in order for something to be in equilibrium?
No.
Why not?
Because with the rotating table, it's not an equilibrium.
Exactly. Exactly. Rotating table, F net equals 0, not an equilibrium, right? So there has to be something else that also has to be true in order for equilibrium to happen. So F net has to be 0 and something else. Does anybody know what that and something else is? Are you thinking, if I do, then I wouldn't be sitting here so frustrated with you, Ms. Garbling? Is that the case? Is that what you're saying? Yes, yes. Yeah, yeah. Something. So I'm going to say an additional condition must be met. Ooh. What's up?
That doesn't explain much.
Not yet. We haven't said what that condition is.
I know.
Is that frustrating?
Just a little.
Okay. Good. I'm glad. We're going to do a little lab. Because that's always fun, right? All right.
Something.